Okay. Well, I'll go through this very quickly because you know all this anyway. So this is the decimal number system is what we use obviously to count with. Okay. And that is based in kind of thousands, hundreds, tens, and units. But is the binary system we use for a computer, and that is why we have 3 bytes of color, means up to 255, is because that means in each byte there are 8 bits, and 8 bits can come to a maximum of 255. So if it's like 128 and 64, 32, 16, 8, 4, 2, 1, all that together equals 255. And the smallest of that is 0, 0, 0, 0, 0, 0, 0, 0, and that is 0, of course. Okay, so that's how we have 256 values for each byte. Okay. Let's go on next. Now, have any of you ever created web pages? Produced web pages? Yeah. Typically in a web page you'll see something like BG color equals followed by something like this, hash 00FF00. What color would that be? No. Oh, you were right. I'm sorry. Yes, it is right. It is. Just tell the others why is it that it's green?
The first 2 bits represent R, and the second 2 represent G, and the
that's right. Exactly. Yeah, that's right. So that 00 represents the red, FF represents the green, and 00 represents the blue. Okay. So why does what does FF? What is the value of FF?
255.
That's right. Exactly. Okay. You all know. I think you must all know hexadecimal. Do you? You know that basically hexadecimal is, whereas binary has units of 1 or 0, decimal has units of 0 to 9. Hexadecimal has 0 to 15, and 15 is represented as F. Okay, so basically when you say FF, you mean 15 times 15 15s plus 15, okay, which equals, of course, 255. Okay, it's just a convenient way that we use to represent color. Okay, and you'll see that on virtually every web page, is how you can actually use these numbers to represent the colors of the red, green, and blue. Okay, so I'll just won't label this point too much. Okay, these are just so the hexadecimal and RGB values of very typical colors there. Okay, so now let's just have a let's just do a new here. Okay, so I mean, if the way we represent pictures is basically it is sequences of dots. So if I do some, sorry, these are not very good. So if we do the letter T, okay, that is, I mean, I can represent that by a sequence of dots, okay, and then for each square there can be a color, okay, inside that object. Now, for example, on this image you have, it was kind of 5 by 5. No, sorry, I'll put this to, I don't know how to put that to the back. Okay, let's do a new slide. Okay. Oh yes. Let's just delete that. Oh, how do I delete it? No, I can't delete it. All right, I'll just start again. Okay, but if you have an image which is 5 pixels by 5 pixels, okay. So if we have 5 by 5 pixels, how many bytes would it take to represent that in terms of full color? if I want, so I've got 5 by 5, okay. So I've got an image which is 5 by 5. So I've got 1, 2, 3, 4, 5, 1, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, got an image of 5 by 5, okay, and each pixel can have, its full colour. So how many bytes do you need to be able to produce all the colours the human eye can see? How many bytes per pixel? How many? Well, it's 3. So it's 3 bytes per pixel. So 5 by 5, that's 25. That makes 75. 75 bytes altogether. Okay. So now, so that's kind of 5 by 5, which will be tiny, wouldn't it? They'll be absolutely small, very, very small. So if we had it something more like 100 by 100, okay, how many, and that has 3 bytes per pixel as well. That effectively means that it would take, that's 10,000, 30,000 bytes, which is how many K? 30, which is 30K, okay, and that's 100 by 100, okay, which on this screen, I mean, it's not very large. I mean, how big is a typical computer screen? No, in terms of pixels, sorry.
800 by 600.
Yeah. If, even if older ones, it's kind of 800 by 600. So if we work that again, so 800 by 600, that's, my God, how much is that? 600. It's like 48. That's 0, 0.
480,000.
That's right. Thank you very much. 480,000. 480,000. So that is 480K. Okay, for 800 by 600. And of course, on a much larger screen, 1024 times 786 equals, well, that'll be much higher still. So that'll be something like, it's bound to be approximately 800K. Okay, so that's how much space we need. So now, think about, well, of course now everybody has broadband, and so therefore a lot of people have broadband, so it makes it very easy to transmit quite large things very quickly. But it's still, as you can see here, these are very large amounts of data, okay? And so what, typically, do we send kind of images like that? Would typically an image this size, would it be 800K if we got it off the internet? No. So it is compressed. Exactly. So therefore, because these things are just so large, we need to have compression. Okay. Now, there are basically, well, I'll be coming on to this shortly, okay, there are 2 forms of compression typically used in image compression. One is called lossless, and the other one is called lossy. Okay. Typically, which form of image compression uses lossless? Which kind of type of file uses lossless compression?
Text.
No, I'm just talking about proper image files.
Okay, image file.
Image files, yes. Well, I'll just close this door.
GIF.
Yes, exactly. GIF files are typically lossless. Okay, although they only have 256 colors, the compression that you do does not actually remove any information from the image. Okay. However, if you use JPEG, which is lossy, what it does is it actually tries to eliminate information in the image which it believes your eye cannot see. Okay, that's the big difference between the 2 forms. Because as you see, I mean, if it takes 800K to represent a full screen, and if you think that, typically digital video will be having 25 frames per second, the amount of data that you would have to transmit is absolutely enormous. So therefore, that is why techniques of compression have emerged. Okay. Now it's maybe not so important as it used to be because of things like broadband, but in times when you only had modems, it was really important that compression was working. Okay, so let's go forward.